All right, great. So today we are very happy to have Roberto Emparan from Barcelona. He's going to tell us today about black holes physics. So please.
Okay, thank you. Thank you for the invitation to talk. Of course, like everyone, we're missing the days when these talks took place in person, but let's hope that within well, less than the time that we've already been locked down or almost locked down, that we can go back to something that resembles normality. So, well, in this talk, let me first say, I mean, I was asked to give some sort of overview of work that's been done on black holes in diverse dimensions from 4 to higher in recent times, and then discuss open questions. But of course, this is, I think it's a fairly tall order because this is a huge subject. So I won't be able to provide anything that's close to an exhaustive review. First of all, because well, I haven't been following all of the work that has been done, at least not close enough to review all of it. Then I have, of course, my own personal biases and things that I like better or I understand better. And then, well, this is just kind of apologizing in advance. It's preemptive apologies that there's many things that I won't be mentioning, and some of them are important results and subfields. I won't make any attempt at crediting everyone for work that's been done, because then I would be filling my slides with names. And then, of course, if you have any comments or suggestions for things that you think should be mentioned, or results or people who should be mentioned, I will be very, very happy to hear what you have to say in this respect. Okay. So, well, I think that the main topic, the main theme of this talk is going to be that if there's something that we learned in the last 2-3 decades or so, is, well, first of all, it's something that we already knew, that black holes, they are scarce if you're in 4 or lower dimensions. And also, if you don't have a cosmological constant, or even with a cosmological constant, there's not that many black holes that are allowed. But well, when you relax this, when you go to higher dimensions, or when you include the possibility of having a negative cosmological constant, well, suddenly a Pandora box opens, and many, many new possibilities arise. And then, well, I will begin, almost the first half of this talk will be kind of giving you my understanding of why things are like this, why black holes are so scarce in lower dimensions first, then I will discuss the cosmological constant, and then why they are much more abundant when we go to higher dimensions. Okay, so this is just dimensions independently of the cosmological constant. And then, of course, well, I mean, a main or a fairly obvious reason that you may think for this state of affairs, I mean, something that's the most obvious explanation is that, well, as you go to more dimensions, you have more degrees of freedom in your theory. The graviton has many more polarizations, so it's just natural that you get more possibilities for black holes. But I don't think that this can be actually a good explanation, because it's not the case that in most of the new solutions that we have been studying, it's not the case that all of these degrees of freedom are excited or active. Many of the solutions have the same, they depend on the same number of coordinates. So typically in the solutions that we have that there's many cyclic coordinates that nothing depends on them. No, the metric doesn't depend on them. So even with, say, solutions that depend on just non-trivially on just 2 coordinates, like in the case of the Kerr solution, even in this case, we have many, many more solutions in higher dimensions than in 4. And then, of course, this I mean, trying to explain things in terms of the larger number of degrees of freedom, this cannot be the reason that including a negative cosmological constant gives us so many more classes of black holes and so much larger variety of dynamical possibilities. So why is the reason then that we get that we have this difference, that going to higher dimensions or including negative cosmological are such big game changers? Well, I think the reason is, or at least much of the explanation can be given in terms of, well, thinking of scales. Of course, thinking of scales is the main thing I think that we have to do, or that we do when we teach our students how to think about physics. Probably the thing that we have to insist most to them is that they should think when they're facing any problem in physics, they should think about what are the scales that are relevant to this problem, how they organize themselves, and how you get different physics depending on which range of scales you're in. So that's going to be a main thing that I'm going to be discussing for the next minutes. So just to summarize, what's been known for many years is that in 4 dimensions and without a cosmological constant, I will not discuss much the case of a positive cosmological constant. It doesn't really make much difference for what I'm going to say relative to the case where there's no cosmological constant. So black holes in 4 dimensions and asymptotically flat, they are all kind of plump. They are fairly rounded objects. They are never long. This is what I mean when I say that they are round, is that they are not much longer in one direction along the horizon than another directions. Okay. They also not only approximate spheres geometrically, but also topologically. They have to be spherical. They are stable, at least a large majority of them. The Schwarzschild solution, Kerr solution, and other solutions are all dynamically stable. They are hairless, and they are rigid, meaning that they have a lot of symmetry. But when we go to higher dimensions, or we include a negative cosmological constant, then we find that, well, these things don't hold anymore, at least not necessarily. We have black holes. We have examples of black holes that violate any or all of these conditions. Okay. So I will begin going one by one over these properties of 4-dimensional synthetically flat black holes and how they change when we include a negative cosmological constant or go to higher dimensions. So we'll begin with this idea that black holes have to be plump around this and not much longer in one direction than others. This in 4 dimensions, in the case of, say, the Schwarz and the Kerr solution, this is a consequence of the bound on the angular momentum of the Kerr black hole. Because if you have a Schwarzschild black hole, well, the length scale, the characteristic length scale of the black hole is the one that we can construct out of the mass. That's g times m. That's twice this is the Schwarzschild radius. But if we have a rotating black hole, well, the angular momentum cannot be much larger. So it cannot give us a scale that's much larger than the mass. Okay? So essentially, we only have one length scale along the horizon in this case, which is the reason that the Kerr black hole can never be much larger than in one direction than in the other. You may wonder what happens if we go to a near extremality. It gives us another scale, but in this case, that's a scale that's not along the horizon, it's orthogonal to the horizon. And I will not say much about it, even if it's also a very interesting property. Now, so why do we have this Kerr black hole bound? Is there some simple kind of intuitive way of understanding why we cannot take the spin to be much larger? And what would happen if you try to spin up the black hole? What happens when you take a kind of a bunch of dough, a ball of dough, and then you spin it up like you're going to do if you're going to prepare pizza? Well, it's going to spread along the plane of rotation, and then it's going to be much longer in some direction than the other. Okay, you guys are in Chicago, so you know about pizza. So why are 4-dimensional black holes not so much like pizza? Well, you may think, well, the reason that not pizza, but say stars don't spin up, you cannot overspin them up too much, is because if you try to do that, well, then the centrifugal forces become too strong, and then the star just explodes. Centrifugal forces just trigger some instability, and the star breaks up. But in this case, it's not because of instability. I mean, if you try to spin up the Kerr black hole, you don't encounter an instability. What you find is that, well, at least at the level of solutions, what you find is that you would encounter a naked singularity, but that's not an explanation of what happens. That's just a statement that you cannot spin up the black hole. A better argument or a better way of trying to see what happens is what actually Bob Wald started doing many years ago. What happens if you try to spin it up by throwing particles? And what he found is that if you try to do that, you always fail. You can only get, well, marginally closer to the bound. But for one reason or another, you always fail to spin it up. Maybe because you're missing your black hole, or because there are repulsive forces that would repel some spin. So that's, I mean, you're not allowed to do it, to overspin it. So that's a kind of a physical mechanism preventing it. But is there some way of understanding, another way of understanding why we cannot have black holes which are longer in one direction than the other? Like if you try to spin up, assuming that if we were able to spin up the black hole much more, it would become much longer in one direction than the other. So why can't we have this? Well, the reason is essentially the same reason that we don't have black strings nor black brains in 4 dimensions. These are horizons which are really much longer in some direction than the other. A black string is something that would be infinitely extended in one direction and compact in the other directions. And why can't we have black strings or black brains in 4 dimensions? Well, if you think about it, if you had some black string, then that would be translational invariant in one direction. So gravity would be only kind of active or attractive in the transverse direction. And then, well, if you had a black string, then this means that your gravity would be essentially a 2+1 dimensional gravity. Gravity in 3D. Gravity in the directions orthogonal to the black string, that would be 3D gravity. And then, well, we know that there are no black holes in 3 dimensions if you're trying to solve the Einstein equations in vacuum. Okay. Now, why is this? Let's again question, why don't we have black holes in this theory in 3 dimensions? Well, again, it's a matter of scales. People often say that the reason that we don't have these black holes in 3D in a centrally flat vacuum gravity is because, well, 3D gravity, pure 3D gravity is a topological theory. There's no attractive force because there's no gravitational waves, or gravitational interaction is something that's pure gauge. So that's something that's often said, but I don't think that that's the best explanation. I think there's a much simpler explanation, which is to say that in 3 dimensions, the product of g Newton times the mass is dimensionless. If you're given a mass, you cannot construct any classical length scale out of it. So if you cannot construct, if I give you a mass and then you cannot construct a length scale, well, there's no place that you're going to be able to, where you're going to be able to put a horizon. There's nothing telling you where the horizon should be. So there's no place for a horizon because there's no length scale that would be associated to this horizon. So that's the reason that this theory doesn't have any black holes. Now you can have black holes in 3 dimensions, you can have them, but then you have to do something else. You have to introduce some length scale. And there are different ways of doing it. One of them is by introducing a cosmological constant, in particular a negative cosmological constant, if you also want this cosmological constant to give you some sort of attraction. Then that's something that you can do, and you know that in this case you can get the BTC black hole in ADS3, but you can also get black holes if you include, for instance, some well, quantum effects. Because in that case, you can construct a length scale, that's the Planck scale. And well, if you include quantum effects, it's possible to have black holes in 3 dimensions, which are asymptotically flat. I'm not going to discuss them, but that's also an interesting possibility for, as I say, evading this obstruction. So then, well, if we go to higher dimensions, then these problems disappear. Because the gravity in the directions transverse to a string, that would be say in 5 dimensions, a black string in 5 dimensions, the gravity in the directions orthogonal to the string, it's effectively 4-dimensional gravity. That's attractive, and then you can have that well, black holes that are elongated along one of the directions. And if you go to even higher dimensions, then you get not only black strings, but also black brains and well, all the other possibilities that well, all this extra room allows. Now, we not only can have these infinitely extended black holes, but also we can have horizons which are very well extended, but not infinitely. Okay. So for instance, we can also, in 6 or more dimensions, in this case, in 6 or more dimensions, we can spin up the black holes and then we can spin them up as much as we want. Because in this case, well, what they do is they spread along the plane, gravity in directions orthogonal to that plane. That's a 4-dimensional gravity, effectively, at least very close to the axis of a very pancaked object. Gravity behaves in a 4-dimensional way. So in that case, yes, you can have that kind of black hole which is extended in one direction, in 2 directions, and much less extended in the other directions. And you can also have black rings, which is what you would get if you take a black string in 5 dimensions, and then you bend it into the shape of a circle, and then you spin it up. Okay. All of this is essentially a matter of well, how different scales play against each other in this game. Okay, and not only can we have this, I will say more things about the other black things that we can construct in 6 dimensions, essentially following the same ideas. So that's increasing the number of dimensions. What explains that if we have a negative cosmological constant, we can also have horizons which are more extended in one direction than in some directions than in others? Well, we already saw that having a negative cosmological constant, it's something that allows for the existence of black holes in 3 dimensions. And the reason that is what I said. First of all, these black holes are black holes whose characteristic size is of the order of the cosmological radius. You need a negative cosmological constant because if it were positive, then you wouldn't have attraction, and there has to be some attraction. If you're going to trap objects inside the horizon, there has to be clearly some sort of attraction, and that's provided by the negative cosmological constant. Now, if you go to 4 or more dimensions, well, in this case, you have this attraction that the cosmological constant provides. It's helping you. If you didn't have the cosmological constant, then, well, there wouldn't be this length scale, and you wouldn't have, I mean, this is what we already saw, that in d equals 3 or 4, I mean, you cannot have extended horizons. But if you have a negative cosmological constant, it gives you this length scale that we needed in 3 dimensions, but it also gives you attraction. And it's an attraction that acts everywhere. It's homogeneous attraction. Okay? ADS, it's a homogeneous space. It's a space that, well, you have this additional pressure, this thing that tends to make things collapse. It acts everywhere. So this is the mechanism that allows you, as I was saying, to have ADS black holes in 3 dimensions, but also planar anti-de Sitter black brains in 4 or more dimensions. Because in this case, you can have this effect, this attraction that's not localized. I mean, the cosmological constant, in a sense, is helping the attraction that the mass would provide even in 4 dimensions. It's providing extra attraction, which allows you to have these infinitely extended horizons in 4 dimensions, which can be planar or they can even be hyperbolic, which is kind of well, pushing it one notch farther. So this is I think it's well, the simplest way that I have that I can provide for understanding why black holes in higher dimensions or with a negative cosmological constant, why they don't have to be plump, they don't have to be rounded. So now let's move to this other property that 4-dimensional black holes have, that they have to be topological spheres. Maybe this is going to be a little less intuitive than what I said before, but essentially the idea is that, well, in 4 dimensions, what happens is that well, there's a theorem that applies not only in 4 dimensions, but in all dimensions. These are the theorems of topological censorship, which they say that under suitable conditions, it's a null energy condition, if I recall well, that causal curves that go from scri minus to scri plus, they can be deformed, they can be pushed, they are homotopic to another curve at infinity. This means in 4 dimensions that you cannot, if you have some toroidal black hole, then, well, you could take one of these causal curves. It can be a light ray, it could be a time-like curve as well, but say that you throw a light ray that goes through the hole in the torus and then threads it and then goes to from scri minus to scri plus. Then you couldn't deform this light ray to infinity, so this is forbidden. it's forbidden in 4 dimensions. But if you go 1 dimension higher, this is not forbidden anymore, because in 5 dimensions, if you have, say, a surface with this topology, S1 cross S2, then in this case, you can take this thread, and then you can move it in the additional direction, in the 5th direction that you have, and then you can move it, and, well, you can take it to infinity. Okay, so there's no obstruction. This topological censorship is no obstruction to having horizons of this kind in 5 dimensions, which we already mentioned, they actually exist in the shape of these black rings. And if you go to even higher dimensions, well, you can have black rings with this topology, and you can the constraints from topological censorship are well, way weaker than they are in 4 dimensions. It's not only this; there's many other topologies that are in principle allowed by the theorem. Let me also say that in ADS we have these black branes, 4-dimensional black branes, where you can take this planar black brane and then compactify it. You can compactify the directions along the plane into the shape of a torus, 2 circles. And then topological censorship doesn't forbid this, because you also have, in this case, this structure of this toroidal structure at infinity. So, I mean, there's no obstruction. Okay? You can remove the curve from one place to the other. The difference in asymptotic flat is that you don't have that that S1 cross S1 at infinity, whereas here, in this case, in ADS, for the ADS black range, you do have that. Now, black holes in 4 dimensions, they are stable, dynamically stable. The source solution is proven to be stable. The proof of stability of Kerr is maybe not complete, but I think there's no reasonable doubt about it. Proves to be stable, at least in all numerical simulations that people have done. So why is this? Well, here I don't have much new to say, but essentially it's the rough intuition that the horizon is kind of a soap bubble. And then if you have a soap bubble, this is that every kid knows that if you have a soap bubble that's kind of round, that's stable, but if you try to stretch it, then it breaks. So long soap bubbles are unstable and round soap bubbles are stable. So, well, what happens then when we have these long black holes in higher dimensions, like black strings or black branes? Well, these long black holes, which are much longer in one direction than the other, so we want to have one long direction and then some short directions. Well, they have been known to be unstable, to pinching for a long time. This was something that was discovered by Ruth Gregory and Ray Laflamme. I think that Ruth was actually a postdoc in Chicago at the time. So this instability that they found well, almost 30 years ago, it's essentially that what you would expect also some fluid, the surface of a fluid jet. What does a fluid jet do? Well, you just go to your kitchen sink and then you let it drip, and then you see that it develops ripples and then it breaks. So this is the idea of the Gregory-Laflamme instability, that black strings also develop these ripples. They found them by doing a linear perturbation analysis. And yeah, so I mean, these are very simple black holes that exist in higher dimensions, and in contrast to the black holes, vacuum black holes in 4 dimensions, these are unstable. And this is not only a property of infinite black strings or black branes. Other elongated black holes, like these pancaked black holes that rotate very fast in 6 or more dimensions, we also know that they are unstable, that they are unstable too. I mean, it's not that they become peanuts. This is more like if you take a ball and then you pinch it at the center. Okay, so this is rotationally symmetric. These black holes, they have this kind of instabilities, which are at heart, they are the mechanism that's driving them is the same mechanism as the Gregory-Laflamme instability. Now, this instability, it's also quite interesting in that it gives you. So the instability appears only when the rotation is sufficiently large, when the black hole is sufficiently elongated in some directions than in others. But the instability begins, I mean, it's a phenomenon that happens when some frequency of a perturbation frequency, which is initially stable, so omega squared would be positive, then omega squared goes to negative. It crosses to negative when you spin the black hole up. So at some point, omega is going to go to 0, and then this means that that value of the parameters, when this you have this mode of 0 frequency, that's a 0 mode. That's a static or stationary deformation of the black hole that gives you another solution. So you can get out of this, or branching out of these marginally unstable solutions, you can get branches of inhomogeneous black strings, or also black holes, rotating black holes. These are, well, we can call them inhomogeneous horizons or bumpy horizons. And they have been constructed for the black strings, but also for rotating black holes. I will say more later about how they have been constructed. So this is something that usually is not mentioned, because in 4 dimensions, well, all black holes that we know are fairly smooth. It's difficult. It can be characterized in some ways, but it's something that people didn't pay much attention to the old times. I mean, the black holes were smooth, but now they can be smooth, but they can also have ripples. They can be bumpy black holes. Okay, so we have that. So, I mean, that's another property that we've seen how it changes as we include this, as we change the rules of the game. Higher dimensions or negative cosmological constant. Now let me say something about hair. That black holes in 4 dimensions, they are famously hairless. By hair, I mean that they don't support matter fields, say scalar fields or other fields outside the horizon in static or stationary configurations. Okay, I'm not referring to the uniqueness theorems so much. The uniqueness theorems are the uniqueness of the Kerr black hole. That's I want to distinguish between uniqueness theorems and no hair theorems. But why is the reason? What's the reason that black holes have no hair? Well, the reason is that black holes have they have their own taste. They don't like to sport hair. If you try to put hair on them, on these 4-dimensional black holes, at least without a cosmical constant, the black hole either swallows the hair, it sucks it up, or expels it, it repels it. But the black hole, I mean, it's like if you've ever had a baby of your own, when you try to put something on their head, like a cap or some bonnet or something, well, they will immediately take it away. I mean, they don't, well, they may chew it as well. But so black holes have this kind of behavior as well. What's the reason for this? Why does the black hole, well, the reason that it wants to suck it up, that's clear, because black holes want to swallow everything, but the reason that they also repel hair may be a little less obvious. But if you think about it, it's fairly natural. So this is, if you consider, say, some test scalar field in the presence of a black hole, say the Schwarzschild black hole, then you can write down the equation for the scalar field in terms of, you can write it in terms of some effective radial potential. You can write down something like a Schrödinger equation with an effective potential. And the effective potential has this shape. It goes to infinity over here, and it goes to the horizon. This is the tortoise coordinate that you have. So the horizon is down there. So I said you expect this potential to go to 0 at large distances to the left, because this means that things tend to fall inside the black hole. The reason that you also get this potential over here, which is kind of repelling things over here, is that, well, this is a gradient, a potential that appears because if you try to put something, say a scalar field, into something that's well, very close to the horizon, then well, the field develops large radial gradients. Imagine that you're, say, in a spherical symmetric configuration, then, well, in order to compress the field, you have to, your radial gradients grow very large. You can also have centrifugal barriers, which also behave in the same way, like 1 over r squared in all dimensions. But this barrier is there even in the absence of angular momentum, even for S waves. And as I say, that's the radial gradient. So what happens now if you try to put some scalar field configuration over here? Well, it won't stay put. Either it will want to escape away to infinity to get rid of all of these radial gradients, or it will fall inside the horizon. So there's no place in these black holes for a stable hair. But what happens then if you put now, if you don't let this hair to go to infinity? If you put the black hole in a box, what's the best box that we have? Well, it's a covariant box called ADS. Well, in this case, the box, what it does is that it changes the potential so that the potential now grows as you go to infinity. This is the boxing effect of ADS. And then in this case, you see that well, black hole can, the hair, your scalar field, can condense over here. And then this will give the black hole some hair. Okay. So that's, I think, well, the basic reason that including a negative cosmological constant gives you all of this new playground to try to dress the black hole with different kinds of hair. We get, and this is, if you try to put a scalar field, then you see that you have something that the hair can condense, very much like when you have a tachyonic instability, like in the Higgs mechanism. This is a tachyonic instability. You can actually see it this way. It's a mode, if you study perturbations, it's a mode whose mass squared becomes negative. And well, it's an instability that's different than the Grover-Laflamme instability. Okay? The Grover-Laflamme instability is more like a ghost instability, not like a tachyonic instability. I can elaborate more on this if you want. But let me now move to the next idea that we want to analyze. Is the idea that horizons of black hole horizons are rigid and very symmetric. And well, of course, I mean, you have one person who knows way more than I do about this. That's Bob Ward, who's proven some important theorems in this respect. The mother of all of these theorems is an old theorem by Stephen Hawking, that the event horizon of a stationary black hole and of a black hole spacetime is a scaling horizon, and then he could also conclude that the black hole is axially symmetric. There's extensions of these results to higher dimensions by these people, by Holland, Sebastian Wald, and at the same time by Moncrief and Eisenberg. But well, people have found ways of kind of evading the assumptions of the theorem. And one thing that people did, in particular when trying to, since people discovered that they were able to put hair on black holes, well, then you can think about something, borrow ideas from this concept of a cubole. These are configurations where your matter fields may break some symmetry. In this case, matter fields break axial symmetry. If your matter fields break axial symmetry, and imagine that you have some, your matter field is some charged scalar field. So it has a phase, and then the phase breaks axial symmetry, but the stress tensor, which is kind of the square of the modulus of this scalar field, this doesn't see this symmetry breaking phase. So the stress tensor doesn't break the axial symmetry. And if the stress tensor doesn't break the axial symmetry, then the geometry doesn't break the symmetry. But the whole system, the entire system, is not axially symmetric. So this is one way of having black hole solutions, which don't have this axial symmetry, which only have one Killing vector, the Killing vector, the stationary Killing vector. And as I say, this is one mechanism that people found for achieving this. But there's another thing, other kind of phenomena that you can have in higher dimensions, and with a negative cosmological constant also, which is, and there's something about that theorem, an assumption that's very important, and that's that the horizon is compactly generated, that the horizon is compact. And if you have non-compact horizons, and then we've seen that we can have such horizons when you go to higher dimensions, horizons which are extended, infinitely extended, all the way to, say, the boundary of your space-time. When you have these non-compact horizons, then, well, you can lose and gain generators of the horizon through the boundaries of the horizon. Okay? So these are horizons that extend to infinity, and then you can gain or lose generators to infinity. And in this case, we can have black hole horizons, event horizons, which are not Killing horizons, even if there's some stationary Killing vector in the geometry. This gives rise, I mean, this is something that maybe, I mean, the way that I describe it mathematically, it may sound not very clear, but physically the idea is quite simple. It's the idea that, well, if you have an infinite horizon, then, and this extends to infinity, then this horizon may be connecting reservoirs, infinite reservoirs at different temperatures. You know that black holes are thermodynamical systems. Of course, they have some temperature, and then they can transfer energy along their horizon. And then, well, if you have, as I say, black holes which extend infinitely, and you can have, for instance, a black hole that extends in ADS, you can have a black hole that goes in some directions as a black brane, but then it goes towards the ADS boundary. This is also another infinity of the black hole. It extends to infinity. So here you have some, at the boundary, you have something that looks like a black hole localized at the boundary, which may be at one temperature. Then you can also have this black brane at a different temperature. And if these two temperatures are different, what you're going to have is a continuous flow of energy from the hotter horizon to the colder horizon. And since these are infinite, because this is at infinity and this is also infinitely extended, then this goes on forever. You're constantly getting generators in from one region and then losing them at the other region. Then this is something that you can have. These are configurations that you can have if you're taking the planar ADS, the Poincare type ADS, but you can also have it in global ADS. You can have something that you may want to describe as a black string that extends from one point at the boundary to another point of the boundary. These two black holes that you get at each of the two boundaries, they need not be the same, and they can be at different temperatures. So in this case, what you're going to have is a continuous flow across the bulk of energy from one side to the other. And then you can begin to play. You can begin to play more, and it's in fact, it's a very interesting game to play because, well, what these configurations give you is holographic bulk duals of quantum field theory in the presence of a black hole, in a black hole background. Because as I was saying, here we have the ADS boundary, and on this ADS boundary, here we have a horizon, that's a black hole horizon. It's a black hole horizon that's in the presence of a thermal bath that extends all the way to infinity, and they are connected, they may exchange energy. You can also have other configurations where the black hole at the boundary and the bath that it is immersed in, that they are insulated from each other, or you can even get rid of the bath, and then you would have a hot black hole that's not radiating to a cold boundary. These configurations, they've been studied, I mean, sometimes, well, in some cases, in a few cases, low dimensions, analytically or semi-analytically. If you want to study them in higher dimensions, then you have to do things like, you have to do it numerically or possibly go to an infinite number of dimensions. That's also something that allows you to construct such solutions. These are called black funnels, and these are called black droplets. And as I say, they are very useful and interesting for understanding this phenomenon when you're, particularly when you're interested in having a strongly coupled CFT. Variations of this have also been studied quite a bit recently. Instead of having the black hole at the infinite, at the asymptotic boundary, moving this boundary inside the bulk and then putting it on some kind of brane. That's a game that's been played a lot in the context of well, these double holographic models for reproducing the page curve or radiation in the black hole information problem. This is, again, that same kind of game that people have been playing. More in lower dimensions than in higher dimensions, but in principle, it's also possible to have these things in higher dimensions as well. So, and with this, I kind of finish this discussion of, well, how this negative cosmological constant or higher dimensions allow us to have phenomena which are different than what we had in the old days of 4D without a cosmological constant, with a positive cosmological constant. Let me say now a few things about how we go about constructing these solutions. Yes, please.
If you back up a slide, so are in the dual field theory, are these things that were investigated some time ago called plasma balls? Or are these something else?
Well, plasma balls are typically different. I mean, you may want to call them, but they are not actually plasma balls. Plasma balls would appear, so here you would have your ADS boundary. Then you would put something like a confining bottom, and then you choose your, you can put a hard wall, or you can put an ADS soliton or something, and then you place a black hole at the bottom.
Right.
Okay. So then you have some black hole. It could be localized or it could be extended, but say it's a black hole that's localized at the bottom. So what you would see from the boundary is a ball of unconfined plasma, the confined plasma, surrounded by the confined vacuum.
Right.
Okay. So that's what people usually refer to as a plasma ball.
Yeah. So I'm curious as to what this object is that's got a horizon on the boundary, because I mean, I would imagine if I just took a standard CFT,
yes,
and I constructed some, ball of stuff, it would
yes,
just dissipate.
Yes, but the thing is that here, if this is actually at the ADS boundary, then at the metric that you put at the ADS boundary is whatever you choose, and then you can put a black hole geometry. You can put the Schwarzschild geometry at the boundary, just because it's possible. I mean, that's your boundary condition for the metric. You want it to be, and then you try to see, I mean, you extend or you solve the equations in the bulk with these boundary conditions and see what you get.
So I just put my boundary field theory in ADS for Schwarzschild.
Yes, yes. For instance, you can do that, or even in Schwarzschild. If you do it in, say, in Poincaré, you do it in the Poincaré coordinates. So your horizon, I mean, your boundary is asymptotically flat. Then you can put a four-dimensional Schwarzschild at the boundary. Say that this geometry, that here the geometry that you get at this boundary is the four-dimensional Schwarzschild solution. Then, well, you go about then solving the equations with suitable regularity conditions in the bulk. So you're solving this boundary value problem, which is not an easy problem to solve. It's been solved numerically by Figueras and Weisman using their numerical magic. And well, they found a solution that looks much like this. And that describes a black hole that's, so it describes a CFT, state of the CFT, that's in the presence of a fixed black hole geometry, and well, it's regular on the horizon, the CFT. It doesn't radiate to infinity, and if that puzzles you, then well, we can discuss more about it. But I mean, that's something that was for a number of years a matter of debate. But now we know that these solutions exist as static solutions in ADS.
Right. Does that mean you have a boundary information problem?
I don't think that you really do have much of an information problem here, because these black holes actually, they have infinite entropy because they extend all the way to infinity. So when you have infinite entropy, I think many of the problems of black hole information just don't make much sense. You may still be getting some problem, or you can study the black hole information problem if instead of having this boundary at infinity, you move it into the bulk. You do it like in a kind of a Randall-Sondrum construction. So this would be a brane some finite distance away from the boundary, and then you try to put a black hole on that brane. In that case, that situation gets much more interesting. I will say, I will get back to this point when I discuss open questions, because for me it's a very interesting open question to try to see what's the classical bulk dual of Hawking evaporation. I will get back to this point if you want later.
Okay.
At the end.
All right, thanks.
Sorry, I also wanted to ask, for this black hole in the boundary theory,
yes,
you said you impose field boundary conditions on your fields. Do you impose them? Are you supposed to impose them on like the black hole horizon, or is there?
Yeah, you can. Of course, you can choose what conditions you impose. In fact, you can choose that the field is regular on the horizon. Of course, that means also that your classical bulk is also going to be, because if you're going to solve the bulk equations, what you're imposing is conditions on your On your geometry, you impose it to be regular on the horizon, and that corresponds to essentially to the same thing as Hartle-Hawking boundary conditions on the horizon. You can also choose other conditions, and this is you can choose that the temperature of your black hole at the boundary is different than the temperature of the CFT. This is a bit like going to Bulwer or vacua, which are not Hartle-Hawking, which are not completely regular, and that's something that can be studied, and it's in fact it's been studied, and I think it's also quite interesting to study. So you can choose, and most of the things that you can do for quantum field theory in the black hole background, you can study the Unruh vacuum, you can study the Bulwer vacuum, you can study Hartle-Hawking vacuum, and so on. You can study them also in these configurations. And they have a nice bulk duals, or at least interesting bulk duals.
Okay, cool. Thanks.
So, well, in terms of construction solutions, as I said, well, let me first say what we have done, or what people have done, when trying to trying to find the exact solutions, which is of course well, your initial dream or your initial hope. Then, well, people studied this. People try to find the exact solutions quite a bit in higher dimensions during the early 2000s. And what people tried was, well, what did people use when constructing, say, the Kerr solution and other solutions in the 60s and the 70s? Well, let's try to do that, what people used in 4D, let's try to extend it to higher D. First thing is actually what Myers and Perry did when they wanted to generalize the Kerr solution to higher dimensions, which is to try the Kerr-Schild ansatz. And that's the way that they found their large class of rotating black holes in higher dimensions. And that's it's kind of a one pony trick, okay? One trick pony. Sorry. So it's something that the Kerr-Schild ansatz in higher dimensions hasn't given us any other black holes than the Myers-Perry class of black holes. People tried other things. Already in the 70s, people studied the structure of general relativity, and they discovered that in some cases, the Einstein equations can be reduced to some integrable sigma model that can be solved then using inverse scattering techniques. And well, the vacuum Einstein equations with two axial symmetries, they reduce in 4 dimensions to a two-dimensional integrable sigma model, a principal chiral model. In 5 dimensions, you can also do the same thing. In fact, you can reduce everything to a two-dimensional sigma model that's integrable, but it's only in 5D, 4 and 5D, that this gives you solutions which are asymptotically flat. But people use these methods in order to find black rings with several rotations, black Saturns, black all of these configurations with multiple concentric black rings and rings rotating in orthogonal planes. So that's something that worked very well, and that was very well studied and developed. But it only got you so far, solutions with a certain number of symmetries and not asymptotically flat in more than 5 dimensions. So that's kind of where things stopped in terms of how to construct vacuum solutions exactly in higher dimensions. You may say, well, I don't want just vacuum. I may also want to study to include gauge fields, and then why not go all the way to supersymmetry? And of course, in supersymmetry, which was very well motivated by supergravity and by string theory, there was a lot of work on constructing supersymmetric black hole solutions in the 90s, in the early 2000s. I think, well, I mean, that's when the supersymmetric black rings were found. Later, and the progress has been much slower. There's been fewer solutions that have been obtained and studied. I think that the most important ones are rotating supersymmetric black holes in ADS. The first ones were found by Butovsky and Rial, and people have extended them, and they have this has become a kind of a fairly big topic in recent times, because well, there's been a lot of progress in understanding their microscopics, counting their entropy, using sophisticated techniques from supersymmetry, using localization and other wizardry. instead of black holes, where there's been a hell of a lot of progress, and some of you know this very well, Emil in particular, and his friends in Paris. There's huge families of solutions, supersymmetric solutions in higher dimensions, which are regular and horizonless. And this is the entire field of microstate geometries. There's other things that people have tried to do analytically, and exactly there's been studies of classifying and solving for the geometry near the horizon of extremal black holes, BPS or not. Unduri, Lucchetti, Real, and others have done a lot of work on this. That's just focusing. If you have an extremal black hole, then you have these throats, these ADS kind of throats. You have enhanced symmetry, and then you can leverage this additional symmetry in order to perform a fairly complete, or sometimes exhaustive study of the possibilities for black holes. The problem with that is that very often you don't know how to extend, or if it's possible to extend this near horizon solution to something that's asymptotically flat, or that has some outer zone asymptotics different than just the throat. So, as I say, I think that there's been very little progress in recent years in terms of exact solutions. So people have resorted a lot to approximate methods, and in particular numerical methods, which is something that 20 years ago it was very rarely applied to string theory or higher dimensional gravity. But by now people have become very familiar. There are many young experts on this field who can solve or can find black hole solutions, stationary black hole solutions, that depend on only two coordinates. That's cohomogeneity 2. This is something that can be reduced to elliptic two-dimensional boundary value problem. The main difficulty here is, well, what kind of boundary you have. Is it quadrangular boundary or pentagonal? If the more sides it has, the more complicated your grid has to be, but it's something that people can do these days with fairly moderate resources and time expenses. These are things that these problems can be solved in laptops, in good laptops, in the time scale of hours. Well, there's been a lot of progress on this. When people found that they could solve, that they had this tool for analyzing these problems, there's been constructions of things like I was saying before. Toby Weisman was, I think, the first person to put these methods to good use to construct inhomogeneous black strings, but then there's bumpy black holes, inhomogeneous lattices, droplets, funnels, and then people have taken this into the world of ADS CMT, which is an entire world that I cannot do justice to in this talk. And there's a lot of work that there's an enormous possibility of different behaviors, different configurations, and different dynamics and phases of black holes with a negative cosmological constant and with different kinds of fields turned on. What's harder, nevertheless, is if you want to do time evolution. Time evolution, that's harder numerics. That's not just an elliptic boundary value problem. So the breakthrough here, the watershed calculation, was what Lehner and Pretorius did for black strings. They showed, this is a video that you can find in YouTube. You start with a green string and then you let it kick it, and then it becomes colorful. It develops all of this structure. And well, that's it's a kind of a landmark calculation. It used a supercomputer running for 1 month. Nowadays, people have got quite more sophisticated. All these calculations, they use adaptive mesh refinement, and now there are sophisticated codes for this, developed by Figueras, Lim, and collaborators. But these are very expensive methods. You need supercomputers running for long. Developing the code is something that takes a lot of time. So this is something that it's much less widespread than what I said before of this game of trying to find stationary solutions. Time dependence is still a very hard problem. In some cases, people have been clever enough to find a class of problems that can be solved more simply by evolving along characteristics. That's evolving along, instead of the Cauchy problem of evolving starting from in constant time slices, spaces slices. You can also evolve along null slices, and this is much more efficient, turns out to be much more efficient. The only problem is that if you encounter caustics, then you cannot go beyond the caustics. But I think that the seminal work on this was the simulation of collisions of two shock waves to produce black holes in ADS and that was solved by Paul Chesler and Larry Jaffe. Now that's for numerics. That's not my field. If you want to ask me more about the details, well, I may not be able to give you much more detail. Other people who are not so adept at numerical calculations, we have tried to develop analytical approximations. One thing that you can do is, well, consider, since you have long black holes, long horizons, then you can consider fluctuations of these black holes, these extended horizons, which are long wavelength. So this is something that you can do when you have long horizons, like when you have a black brane. Then you can ask yourself, what happens? Can I bend this black brane into different shapes? Then, well, we found that you can do that. And there's an effective theory, a simple effective theory that allows you to do that. It's what we call the Blackford effective theory, where you're taking these black branes and then you bend them into shapes. And we developed these methods and we constructed approximate solutions for, say, things, black rings in an arbitrary number of dimensions. You can also construct slinkies. And then other black holes, like, well, with other topologies, where you start with a three brane, and then you wrap the three brane, you bend it into a shape of a three sphere, you rotate it so that it doesn't collapse, and then you can get black holes with this horizon geometry. And there's many more that you can construct. More recently, we also developed a new method, which is based on taking the number of dimensions as an expansion parameter. So we expand now, as I say, in the number of inverse of the number of dimensions. This is a method that also gives us effective equations, which are much simpler to solve than the full Einstein equations. This works not only with long horizons, but also with round horizons. And I will not say much about this method in this talk, not because I don't think it's interesting, but because it will be an entirely separate talk. But it's a method that's been very efficient for studying stability and instabilities, and also time evolution of horizons. I will just begin to wrap up and say that one thing that can be studied with this method is violations of cosmic censorship that happen in higher dimensions, but they don't happen in 4 dimensions. The paradigm again comes from the Gregor-Laflamme instability, where this simulation of Lehner and Pretorius showed that here that the curvature is diverging. Now, more recently, we use these large D techniques in order to argue that something similar should happen for black hole collisions in higher dimensions. You collide 2 black holes in 6 or more dimensions with sufficiently large angular momentum. They develop something like they become something like a bar. Then this bar becomes longer, and then when it becomes long enough, the Gregor-Laflamme instability kicks in, and then it breaks up the horizon. Now, this is something that we studied first with large D methods, but more recently, there's been dedicated numerical calculations that show that this picture was actually correct. That you begin with, you collide these 2 black holes, and they develop this bar shape, which becomes unstable. So now I will wrap up and say a few things about open questions and directions. I will discuss just quickly. I will group them into questions about solutions and questions about the new phenomena. About solutions, the problem of classification. If you, 4 dimensions, it's possible to classify black holes. Is it possible also to classify them in higher dimensions? This might be possible in 5 dimensions in vacuum, and Stefan Hollands has done a lot of work on this. The classification is not complete yet. There's a few directions that haven't been solved yet, whether there exists a black lens. I don't think that it exists a neutral black hole with the geometry of a lens space. Breaking axial symmetry, which is something that's possible. It's possible to have black holes without that axial symmetry, but the methods that Stefan used are not applicable there. So I'm not very hopeful for full classification. Well, in 5 dimensions it might be possible, but in 6 or more dimensions, I don't think that we're nowhere near classification of those black holes. But if we cannot classify them, well, I mean, not everything is about classifying. I think that physics more about classifying is about understanding. So can we understand what possibilities there are for black holes in higher dimensions? Well, I think that we know quite well what happens with all of these approximate and numerical methods for studying the possibilities, these different kinds of black rings, different topologies, bumpy horizons, and so on. We know fairly well how to understand this in terms of how the different scales along the horizon play out against each other. We know much less when there's a negative cosmological constant. There's a lot of phenomena that are allowed there that don't exist if you don't have the negative cosmological constant. Much less is known when you add charges, in particular p-form gauge fields. A lot is known about supersymmetric solutions. Supersymmetry is extremely restrictive, and as we said, I don't think that there's much left in terms of black holes to be discovered. Maybe I'm wrong, but that's what I think. And maybe there's still the possibility of well, the methods that we use in to construct exact solutions, they were imported from 4D. Maybe there are other ideas that we haven't still found for studying what happens in higher dimensions and also in antithesis there. About phenomena, there's turbulent horizons. It would be interesting to understand them better. Understanding the singularity that appears in this black string pinch-off, that's a naked singularity, and I think that's a singularity that's universal and it's controlled by attractors. And well, this is something that we've been working on for some time, and I think well, we're hopefully making progress. What's the holographic dual of these singularities? And other different phenomena that horizons can support higher dimensions. We've seen that black holes can have extremely rich dynamics. Everything that you can dream of in quantum field theory, or most of these things, you can then find duals in areas involving black holes. So, is there more things that we can do? I think I have some ideas about that. But now then, there's this final thing that I wanted to say: this idea of using black holes at the ADS boundary to study quantum field theory in a black hole background. There's all of these things that are only partially studied. And then finally, there's this idea: if your black hole at the boundary is not a fixed background, but a dynamical background, then this black hole will interact with its radiation, with the CFT radiation outside it. Can we find then a classical bulk dual of Hawking evaporation? And that's a problem that it's been on my mind for kind of a couple of decades, but maybe now we have found a way of dealing with it. And with this, well, I'll stop and well, I'll apologize for running over for your attention. Thank you.
Great, thank you very much. I wanted to open the floor to see if there are any quick questions. Well, if there's no quick questions, perhaps we should take a 5-minute break, and then we can return, refresh, and then return for further discussions.
Sorry, I would have
sorry.
Maybe I ask a very naive question, but it's related to the physical significance of these solutions. How can they apply to the real world at some point in some sort of random scenario or something like this? So we can understand.
So, I mean, the physical relevance in terms of, well, first of all, there's all the world of ADS-CFT. Okay, I mean, that's if you believe that ADS-CFT can be used in order to describe, say, ADS-CMT. I mean, there's a field that well, still has to find kind of an application to the real world that goes beyond the eta over S. I mean, there was hope of understanding non-Fermi liquids, maybe quantum critical points and so on. So that's still an active problem, and this involves black holes in different kinds of dimensions. Very often they are four-dimensional ADS black holes that would describe planar systems, but they can also be in higher dimensions. So that's one possible physical relevance of this phenomena. Then there's a Randall-Sondrum phenomenology. Well, that depends on what's your take on how viable Randall-Sondrum phenomenology is these days. Like all of the brain world models, they are not much favored by observation, but well, there's still room for them. And well, there's, as I was mentioning, Randall-Sondrum black holes, which is something that I was quite actively involved in a couple of decades ago. Many of us were working on brain worlds back then. But I think that also, well, now for me, I mean, there's also this interest of using them for holography, for understanding properties of Hawking radiation. Now, whether that's something that we're going to observe, I don't know. But then there's also, I think, there's a number of things. Of course, higher dimensions, if we want to see them realized, well, I mean, they better be fairly large extra dimensions. And again, that's something that's not much favored by experiments and observation. But there are other things that we have learned. I mean, for instance, this thing that, well, you have black holes that as you spin them up, they become pancaked and then they become unstable. That's very similar also to the physics that we encounter in neutron stars or in stars. What happens in that case is that, well, the gravitational force is not strong enough to balance the centrifugal repulsion. Very much the same physics happens for these higher dimensional black holes. So in a sense, I mean, we're kind of, I mean, even if it's in higher dimensions that we're working, very often the systems that we study, since we impose a lot of symmetry in the additional dimensions, everything reduces to an effectively four-dimensional system. With the additional dimensions, even if they are non-compact, they kind of play a passive role. So very often we're solving same equations that we would solve in 3-4 dimensions, but well, we also have this other interpretation. The physics is kind of the same kind of physics. It's not giving us predictions, if that's what one is after, but I think it's giving us a better understanding of how gravity behaves. And also, I mean, for instance, understanding why in 4 dimensions, well, you have black holes which are always round. When you collide them, well, you always form another bigger black hole. You can never a singularity, a naked singularity. It's not that in a new prediction, but I think that at least for me, it's giving me a better understanding of, I mean, understanding how things happen when you change the number of dimensions. For me, it's also giving me a better understanding of why in 4 dimensions, they work the way they do, which is sometimes quite surprising.
Very good, thank you.
All right, well, let's thank the speaker one more time.